is the most abstract of all of the there we go, abstract of all of the sciences. So for the opener, everything should be active. I just double checked in Canvas, make sure I didn't forget to click something.
You got a pencil?
Oh, I had a whole bunch of them. Maybe. I was gonna say maybe. For this opener, we've talked about this a little bit just because I knew it was coming up. Atoms want to have what's called a full outer shell. Okay, we call the outside shell the valence shell, and that's how they talk. They want to be like their closest noble gas. And when we did the SPDF stuff, when we did the shorthand, the thing in brackets, that was the previous noble gas. Sometimes it's the closest, and sometimes it's not. It was the thing that all the way on the right-hand side, the noble gases, which is 8A. With the exception of one of them, how many electrons do they want in the outside shell? 8. That's right. It's called the octet rule. There is an exception. Well, the thing that, and I'm not the one that's in charge of writing the tests, but one of the things that in previous schools that I always like to do is trick them and say, what does the octet rule state? And one of the answer choices was that they want 8 electrons in the outside shell. That's not 100% true. Most of them do. If I pull mine up here, these 1, 2, 3, 4, 5, 6, these 6, yeah, they want 8. But helium wants 2 because the first shell is full with 2. Every shell after that is full with 8. And so octopus, octagon, oct, the prefix does mean 8, but the octet rule doesn't necessarily mean it wants 8. It just wants to be like that closest noble gas. And in the case of hydrogen, helium, lithium, beryllium, and boron, the magic number is 2. So there is an exception, and unfortunately in this class, there's a lot of exceptions in chemistry, which makes it a little bit trickier. So most likely, yes, that number's 8. Yeah, but it could be 2. There is an exception. Ooh, that's frozen. I have to unfroze it. Let's see, who missed their test yesterday? According to this, when I checked you guys, and like I said, I had to go back and hand grade every single test. According to this, Luke, you missed the test. Braden's remote, and Jeremiah, she just came back. Unless you did it since I checked this yesterday, which I have to go back and hand grade them, you missed the exam yesterday, and you do need a periodic table. And yes, you can use your review. You were very nice to y'all on that last test. What do I need to get rid of? There we go. Did anybody else need a paper version of this? I have them. I did not. They're right here. Okay, everything else is in Canvas. Like I said, in my opinion, we're doing these things out of turn. We're going to go back and we're going to talk about ions. All an ion is an atom. Before, it was different numbers of neutrons, which were isotopes. Ions are the same element. Can't change protons. So same protons, same neutrons. What's different is your number of electrons. And we have 2 major types of ions. And I'm going to tell you like the official, how you're supposed to tell them apart, and then how I seriously remembered it when I was your age. Which is stupid, but it stuck with me. Even near on 30 years later, I still remember it. So anions have gained electrons. Now, first, what's the charge of an electron? Is it neutral, positive, or negative? Negative. So if you gain an electron, are you going to be more or less negative? More. Okay, so anions have brought in electrons to be like the noble gas. Anions tend to be nonmetals, which is not on the slide. They tend to be nonmetals because they gain electrons, they gain a negative charge. However many electrons they gain, that's how negative they are. Cations tend to be metals. They tend to lose electrons, and if you lose a negative charge, you're going to become more positive. Now, this is a stupid way that I remembered it. And I mean, yeah, it's stupid. You may not agree with the way that my brain processes, but and I still do like cats. Some of you probably hate cats. But I mean, I like cats. We used to have a whole bunch of them. We used to have like 8 of them. I could. Well, it's just because my mother-in-law passed away and we sort of inherited her care on the cats. It was not my choice. They stayed behind when I moved. But so I like cats, and so to me, cats were positive. Besides, the letter T is a plus sign. Cations are positively charged. They have lost electrons to have less of a negative and more of a positive charge because regular atoms are neutral. Anions, so for me, and this is the really stupid part that my brain processes, but at the time I hated onions. I know onion and anion are not the same thing, but if you write out the word onion, that literally makes it an anion. Okay, I love onions now. I think they're great, but at the time I hated them. I don't care how you keep these things separate. Y'all, it's not cation. It's cation. It is anion. It's not anion and cation. It's cation and anion. Cations have lost electrons to be positive. They tend to be metals. Anions have gained electrons to be negative. They tend to be non-metals. There are a couple of exceptions, but that's the generic rule. So most metals, I don't have the notes page in front of me to make sure. I tried to underline stuff when I was building this last weekend. I actually did you guys instead of first phase first. No. But I'm telling you, you're going to end up having to know this, that metals, they tend to lose electrons to become positive. Those are your cations, and non-metals tend to gain electrons to become negative, and they are anions. Yes, there are some exceptions. Now, group 8, no, this slide's not on your stuff. I just know that this is important. Group 8, all the way on the right-hand side, these, the noble gases, they're inert. They have a full shell. Most of them don't want to react with anything. Can we force them to? Yes. Specifically in the case of xenon. Xenon chloride is used to freeze them shut instead of burning or cauterizing them shut in the medical field, but you have to force it to react. Most of these, you can even run pure electricity through it, and they don't care. They just glow. That's all they do. That's what a neon light is electrified noble gases. They just glow. Helium is pink, neon is orange, xenon is purple, argon is green, krypton is blue. That's what a neon light is. It's electrified noble gases. But other than that, they don't have to react. Specifically because that outside shell is full. They're not looking for anything extra. And you can literally bombard them with electrons. They don't care. It's just what color it turns into. You're thinking of Superman and kryptonite. Kryptonite's not real. Krypton is. It's just the color that it turns into. I didn't make it. This is what happens. So the part that you guys do have, your representative elements, group 1A, the alkali metals, they're all going to be positive 1. And so on your periodic table, and I couldn't fit everything on one slide. Okay, so when we did our colored periodic table, up top, we should have done +1, +2, +3, ±4, -3, -2, -1, 0. And if you missed the day that we did this, I need to reprint these out. I accidentally threw the whole set of them away. You need to put what are called your oxidation charges up top. Everybody in group 1, straight down, when they make an ion, they gain a +1 charge because they have 1 electron And these things are lazy, just like people. They do the shortest path possible. And if they have one electron, most of them, remember there's the exception, they want to get to 8. And it's much easier to lose 1 than it is to gain 7. Whatever is the smallest number is what they're going to end up doing. Group 2, so from beryllium down, they have 2 valence electrons. And it's easier to lose 2 than it is to gain 6. And if you lose 2 negatives, you become positive 2. Hence, why I wanted you guys to put a +2 on the top. Group 3, they have 3. It's easier to lose 3 than it is to gain 5, so that becomes positive 3. Now, group 4 is weird. The carbon group, carbon has very sticky fingers, and it grabs onto everything it can. It literally has 4 hands. It has 4 valence electrons. Sometimes it'll gain 4, and sometimes it'll lose 4, which is why it is a plus or minus 4. It depends on the situation that it's presented with. But your numbers that we put at the top, which mine is slightly different from the one that you did, the Roman numerals up top, it is 1A, 2A, 3, 4, 5, 6, 7, 8A. We put what we'll call oxidation charges up top, which are these. We're going to use these to build ions. And y'all, I can teach you the algebra if you want me to, or I can teach you the shortcut, which works. You just have to remember how to reduce, which means if everything's divisible by 2, divide it by 2. But the shortcut works. Just have to remember to simplify or reduce. I know so many shortcuts in chemistry. Unfortunately, like I said, in chemistry, there's a lot of but this exception of, which I can't control that. Unfortunately, that's just the way chemistry is. But your Roman numerals are equal to how many outside electrons they have, valence electrons that they have, which is what we're going to go into depth with tomorrow, these valence electrons. That's how they talk. It's literally their language. It's like a puzzle piece. It's how many little nubbins they have sticking off on the side. Group 5, -3, they have 5 electrons. It is easier to gain 3 than it is to lose 5. We're either trying to go up to 8 or down to 0, which is the previous show. Group 6, this is your the oxygen group, the C halogens. It's easier to gain 2 than it is to lose 6. You gain 2 negatives, you become -2. Group 7, your halogens, your salt formers, fluorine down, some of the most reactive things that we have. It's easier to gain 1 than it is to lose 7. Like I said, they're lazy. They just do the easiest, shortest path. And group 8 has a charge of 0. They are the noble gases. They're all the way on the right. They are inert, and they don't want to react at all. Like I said, we can electrify them, and they will glow, but other than that, nothing else happens. These guys are different. Wait till we have the fun of transition metals. We don't start with those. This group in the middle, where we put the orange lines through, they have multiple charges. They don't play by the rules, especially manganese, which is like a PC way to put it. Let's just say manganese gets around. It can be +1, +2, +3, +4, 5, 6, or 7. It reacts with everything it comes in contact with. Fill in the blanks how you want to there. But most of them have 2 types. Iron can be +2 or +3. Copper can be +1 or +2. There are a few of them that specifically have 1 charge. And I can't remember if it's today that we put those. It is today. You do want your colored periodic table. There are 3 of them that are only 1 charge that are transition metal. All of the other ones have at least 2, if not more types. And an oxidation charge is this plus or minus. Does it want to gain or lose electrons? If it's negative, it's gained that many, and if it's positive, it's lost that many. Group 1 and 2 always behave. Group 1 always loses 1. Group 2 always loses 2. Most of the ones in group 3 are going to lose 3. Like I said, unfortunately, there are some exceptions. There are 3 elements that you need to write their oxidation charge directly on your periodic table. They are silver, cadmium, and zinc. Aluminum is going to always have a +3 charge, but it's in group 3, and group 3 should have a +3 on top of it. So you don't have to write that inside the box. But silver, which is right here, you need to put a +1, just like on the top right-hand corner. Do it in pencil on here. Cadmium and zinc, these two, they're +2. Later on, when we actually start naming compounds that have transition metals, these guys in the middle, you have to tell me their charge, either with a Roman numeral or with the suffix of the word. And I do not know how this school wants me to do it yet. All the other schools that I've taught at, we've ignored the ik and the us endings, and we've only used Roman numerals, but I don't know how they do it here yet. Nomenclature can be a little bit difficult. Nomenclature just means how you name them. So like salt, that you guys put on your food, NaCl, it's sodium chloride. That is its name. We call it salt because it is a salt. The stuff that you guys are inhaling, oxygen gas, awesome, but you're exhaling carbon dioxide gas, CO2. I get to teach you not only how to write the formula, but also how to name the compound. But these 3, once again, on your color periodic table, put a little +1 next to silver, a little +2 inside cadmium, and a little +2 inside zinc. You don't have to worry about aluminum because it's in group 3, it's +3. Okay, common ions, numbers of electrons lost or gained, and then the total number of electrons total. I'm hoping that this animated correctly because I've given up trying to write on my board because my board is psychotic. Bromine is in group 7. Over here. You should have outlined it in purple because it's liquid at room temperature. Who's in trouble now? Who's in trouble? Who's in trouble? Hold on, let me double check because everybody's been changing that. Let me just should be. Yeah, he's not here. He's right. Yep, still remote. Okay, thanks. Okay. Anyways, bromine is over here. You should have put a -1 on top of group 7. Everybody in group 7 normally gets a -1 charge because they gain 1 electron instead of losing 7. So -1, even though I just said it, did you gain or lose 1 electron to be -1? You gained. Electrons are negative, protons are positive, neutrons are neutral. Negative how many is how many extra electrons you have. So bromine, its atomic number is 35. So that means originally it had 35 electrons, but if it gained 1, how many does it have? 36. And the atomic number of 36 is krypton, which is a noble gas. Therefore, it's acting like krypton because it's gained an electron. Calcium, which is over here in group 2, it has a charge of +2. So in order to be +2, they gain or lose 2 electrons. It lost 2. I mean, I know it sounds sort of backwards, but you have to remember you're either gaining or losing a negatively charged particle. So if originally calcium had 20 electrons, it has 18. And the atomic number of 18 is argon, which is a noble gas. Well, you're seeing a pattern here. Nitrogen, which is in group 5, has a charge of -3. I know that's a little elevated. I just didn't have time to fix it. So did it gain or lose 3 electrons? It gains 3. And originally nitrogen had 7. So how many does it have if it gained 3? 7 plus 3 is 10. Okay, which is neon. Well, they want to be like this, like, the whole goal is to be inert, to have a full outside shell. If you're trying to figure out how to make a superscript, when you highlight the number and you hit control period, I think, makes a superscript.
Yeah.
I think control comma is a subscript. Okay, so these numbers, they're the atomic numbers down the right-hand side. 5 elements want to be like helium and have 2. Most of your ones in group 2 and the first in period 3 want to be like neon, and then just keep going down. Argon, krypton, xenon, radon, and then I don't even know what that dude's name is. Ogneson. Ognesson, number 118. It's not up there. It has to be scientist's last name. It has to be. The most recent ones that are not up there. Rogenium, Darmstadium, well, Carpernicium, I know that one. Nihonium, I'm sure I'm not saying these right. Fluorovium, Moscovium, that's Moscow, that's easy. Livermortium, Tennessine, and then Ogneson. They're not up there. Like I said, that thing's older than I am.
Oh.
Yes, I guarantee. All those you things above your head, those have been discovered. I don't even know if there is an actual year on that periodic table somewhere. That is an old one. Huh? That's not older than me. I'm older than you. A little bit. All right, so you guys have this guy next. What is hydrogen's symbol?
H.
H. You don't have this?
It's the assembly.
Oh, yes. We're already moved on to the assignment. We're going to go here. Who wants paper version? There. Now I'm lying. God, I was doing it with you. I was doing it first. The first one is done for you. You want to pick the first one? You stole it. Did you all want paper? No, you're good? No, you're good. You're not paper? This says yesterday. Who else wants paper version?
I started on the assembly. Oh, almost done. Cool.
It's not that hard. It's that paper. We okay? No. Paper back here, are we okay? Yes. It is online. I know we're supposed to discourage the touching of papers, but oh well. Okay, so hydrogen is this is the one that was done for you. So you can just tell me the answer since it's on the paper. Hydrogen's in group 1. So that means it has 1 valence electron. Is hydrogen a metal, a non-metal, or a metalloid?
Non-metal.
It is a non-metal. It is the only non-metal on the left-hand side of the periodic table. Okay. Page 4. I didn't do it. I don't know.
I'm taking my stuff.
Okay. Well, if for some reason you're not back, I'll put it up here so my other classes mess with your stuff. So is it a cation or an anion?
Cation.
Yeah, it says it on the thing. It's in group 1, it's +1. It is the only non-metal that likes to be a cation. I said there's some weird exceptions. That one was done for you. Lithium, what's lithium symbol?
Oh,
Li. What group number is lithium in?
4.
1. 4, how'd you get 4? You're just naming stuff. Okay, no, it's over here on the left. It's in group 1. So how many valence electrons does it have? 1. Is it a metal, a non-metal, or a metalloid?
Metal.
It is a metal. That's why do you think we spent a whole day putting this thing together? We keep adding stuff to it. So lithium is going to have a +1 charge. This is a cation or an anion if it's positive. T is the positive symbol. It is a cat ion, not cation, cat ion. I do the first two for you on your homework paper. Nitrogen, what is nitrogen symbol? That's sodium.
Hold up.
N, just an N by itself. Remember, set 3, there's a quiz Friday on set 3, and I went ahead and boosted that to the top of the module. I put the element list back up there. If it's in group, it's in group 5A.
Well, first of all, I'll send it in there. Then if it's funny, it's going to zero.
Okay, anyways, considering that's your cheat sheet for the whole year, way to treat it. How many valence electrons does it have? It's in group 5. 5. Is nitrogen a metal, a non-metal, or a metalloid?
Non-metal.
It is a non-metal. It has to be literally touching the staircase with the exception of aluminum to be a metalloid. To the right is a non-metal, to the left is a metal, except for little hydrogen. So nitrogen's going to have what charge? Remember, it either wants to go down to 0 or up to 8, which is the shorter path.
Anion.
Anion, but negative how much? No, 3. Okay, so once again, I will print off more of those periodic tables, but you're going to have to color code it by yourself. You should have put what we call oxidation charges on the top. I cannot stress how important it is to put those positives and negatives on the top. There are 3 that you should put with the transition metals, the zinc, the cadmium, and the silver. Wow, transition metals are weird. Like I know they can't see it online. These are not the same thing. This is iron 2 oxide, and this is iron 3 oxide. This is rust, and this is not.
It's still iron.
So I know it's still iron, but it's a different type of iron. This one has a charge of +2, and this one has a charge of +3. They are not the same thing. Karen? Okay, so y'all do have the rest of the period. Is there a question? I mean, today's very short. Is there a question where I was getting these charges from? Just keep in mind, if you either want to go up to 8 or you want to go down to 0. Whichever is the shorter path is going to be what you want to do. Okay, let me freeze this. Let me check online. We have 12 minutes. If you finish this in class, awesome, turn it in.